So you can actually define oscillation as the to and fro motion which is periodic in nature. So a force which is directly proportional to the displacement but is actually in the opposite direction of the displacement is known as a simple harmonic motion. So we actually know that velocity is nothing but rate of change of displacement, a motion which repeats itself after a specific interval of time. So that is known as periodic motion. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a new chapter here today, that is oscillations. So what does oscillations hold for us? So the first thing you have to know is what exactly an oscillation is. You might have seen a pendulum which is oscillating from side to side. So what exactly is an oscillation? So you can actually define oscillation as the to and fro motion which is periodic in nature. So you can actually say that oscillation is nothing but the to and fro motion which is periodic in nature, So what exactly is this periodic or periodicity? What exactly is a periodic motion? So you can actually say that periodic motions are motion which is repeating after a certain interval of time. That is, if you take the case of Earth, moving around the sun, then you can say that every 365 days, the Earth completes one revolution around the sun or one rotation around the sun. It circles the sun one time and returns back to its initial position. So the time interval is 365 days, and that is a periodic motion because every year it is continuing again and again. For example, if you are studying in your school, classes or whatever, then at each hour a period changes, right? Which means it is repeating after a certain number of time. So that kind of motion where the motion repeats after a specific interval of time is known as periodic motion. So the to and fro motion which is periodic in nature is known as an oscillatory motion. And what does periodic motion actually mean? A motion which repeats itself after a specific interval of time. So that is known as periodic motion. So again, in the case of a simple pendulum which is oscillating to and fro, it is repeating its motion periodically. That is why it is known as an oscillatory motion. Now again, since you already know what oscillatory and periodic motion are, the next thing you have to know is what is simple harmonic motion, or simply SHM. What is simple harmonic motion? So mathematically, you can easily describe this simple harmonic motion. So you can say that simple harmonic motion, so a force which is directly proportional to the displacement but is actually in the opposite direction of the displacement is known as a simple harmonic motion. Mathematically, we can just write it as F directly proportional to negative x. Or again, F is equal to negative Kx. Again, you might have seen this particular equation in the previous chapter as the spring constant, but here again, it also has relation with the simple harmonic motion, which means that here F is force, X is displacement, and K is a constant. So F directly proportional to negative X. Or in words, we can write it down as So again, in words, we can just simply define simple harmonic motion or SHM as a motion in which force is directly proportional to the displacement, but it is in the opposite direction of the displacement. Such kind of simple motion is known as simple harmonic motion. We have chaotic motion, that is much more complicated motion. That is how exactly a pendulum moves. That is, we have different types of pendulum. We have 2-body problem, 3-body problem. Many types of problems are also there, but we will be only focusing on the simple harmonic motion. That is the simplest case that is there. So again, we can write it as f directly proportional to negative x or f is equal to minus kx. And again, this k is nothing but the force constant in this particular equation. So again, it is very similar to the equation you have seen in the previous chapters, but bear in mind, here in this particular case, it is regarding the simple harmonic motion. So how exactly does this force act? So if you take this case of a simple pendulum, you know that when you initially give it a motion, then it moves to and fro, right? So the thing is that as it moves to one extreme position, the velocity actually changes. The velocity actually decreases, and at this particular point, let's say at this particular point, the pendulum reaches its maximum position. It cannot swing more than anything here. So again, this is the maximum point which the pendulum can swing to. Beyond this particular point, the pendulum cannot execute any more motion. So it means that, okay, this is the extreme position. While reaching the extreme position, the velocity gradually decreases and becomes zero at this particular point, or it reaches a minimum value. And again, as it swings back, the velocity increases and reaches a maximum value at the very center, or what we call as a mean position. So again, at the extreme position, velocity will be zero, and at the mean position, velocity will be maximum. And how does the velocity actually change? You have already studied that without the presence of an external force, or without the presence of force, velocity cannot be changed. So how is velocity being changed here? So the thing that happens is that as this pendulum is moving forward or moving to and fro, there is one exact quantity which you will see in the coming class that is preventing this simple pendulum from executing a uniform velocity. That is, as it is moving in this particular direction, one particular force is acting in the opposite direction. That is, as it is moving in this direction, the force is acting in this particular direction. What is this particular force will be explained through a derivation in the coming class, don't worry. So again, since this particular force is acting in the opposite direction, that is, the displacement is in this direction, but the force is in the opposite direction. That is what simple harmonic motion actually states, F directly proportional to negative x. So that particular force is the one slowing down this or changing the velocity of this particular pendulum. So if there is a change in velocity, automatically there is acceleration. So this simple pendulum will have acceleration and velocity. So next what we are going to do is that we are going to derive an expression for the velocity and acceleration for this particular simple harmonic motion. So first we are going to derive two perfect relations for acceleration and velocity, but how it actually came into effect, what is the full scale derivation, will be discussed very shortly. But before that, let me introduce what is acceleration and velocity in terms of simple harmonic motion first. So we'll start with the equation F is equal to negative kx. But we already know that F is nothing but Newton's second law of motion, which states that F is equal to ma. ma is equal to negative kx. Or simply, A is equal to negative k by m into x. Now, this entire quantity, I'm calling it as omega square. So that, why it is omega square, how you can substitute that, everything will be explained in a derivation that is coming very soon. But for now, I'm calling this particular quantity as omega square. So I'm calling k by m as omega square, which means that acceleration is equal to negative omega square x, where omega is known as the angular frequency or simply angular velocity. So again, a is equal to minus omega square x. That is the first equation for acceleration. And one more important thing, at the very extreme positions, the amplitude will be maximum. That is, the displacement will reach the maximum point. If this is a simple pendulum and this is the maximum point to which it can swing to, then we can say that, okay, displacement reaches a maximum value here. That is, it cannot swing any more further. So at this particular point, we say that it is the maximum displacement that is achievable by this particular simple pendulum. So that particular maximum displacement which is achievable is now known as amplitude. It is known as amplitude. So this maximum displacement is known as amplitude, and we can rewrite this particular equation. So I'm going to take the magnitude value of acceleration, which will be equal to omega square a. So this is one more way you can represent this particular equation. So where a is the amplitude. Amplitude just means that it is the maximum displacement either to one side or to the other side. So that is known as amplitude. And the equation for velocity is given by v is equal to omega into root of a square minus x square. Again, where this particular equation comes from will be derived very shortly, don't worry. But this is one equation you have to know definitely for sure. So here again, a is the amplitude and x is the displacement. So again, if it is at x is equal to 0, that is at the mean position or the extreme position, we can say that at the extreme position, that is, if this is a simple pendulum, this is the mean position where the x value or displacement is 0. And if it is swinging to the extreme position, we can say that, okay, this is the extreme position where x is equal to a. Where x is equal to a. That is, displacement will become maximum and it is known as amplitude. So, when at mean position, displacement is 0. When at extreme position, displacement will be maximum, which is equal to the amplitude value. So, we can say that when x is equal to 0, when displacement is 0, then this x term will be cancelled out because the value is 0 at mean position. Then we can say that v is equal to omega into root of a square or simply omega a. That is, the maximum value or maximum velocity will be attained at the mean position. As I explained earlier, the pendulum which is swinging to the extreme position slows down, becomes minimum value, comes back, achieves maximum value and repeats the procedure. So here again at mean position you will have maximum value. What about at the extreme position, x is equal to 8, automatically v is equal to omega into root of a square minus x square will become a square. So again a square minus a square 0, so velocity will become 0. That is, minimum velocity will be attained at the extreme positions. Now, in order to understand the equation for velocity and acceleration, we have to identify one more equation that is known as a time displacement equation or simply displacement time equation. So what exactly is that? So since a pendulum is oscillating in midair to and fro, or any motion that is executing a simple harmonic oscillation or simply simple harmonic motion can be represented through a simple equation that is like this. So again, in the previous chapter, you have already learned that we can represent equations or displacement equations in the form of wave functions. So you can either use a cost function or you can use a sine function. In your textbook throughout, they have used cost function. That is why I'm using a cost function. You can also use a sine function. It is completely normal. No other problems will be there. But again, in your textbook, it is a cost function. Hence, I've used a cost function. In this particular equation, this x is the displacement. Displacement at any particular instant will be given by the product of A. A is nothing but the amplitude, the maximum value that is attainable. In the case of a cos graph, that is cosine graph, the maximum value attainable will be 1. So A is amplitude, cos is the nature of the graph. It is the nature of the graph or nature of the motion. So it can be a sinusoidal graph, or here it is a cosinusoidal graph, or simply a cosine graph. And omega t is simply representing theta. So theta again is angular displacement. It can be written as the product of angular velocity times time. So again, theta is equal to omega t, right? Or theta by t is equal to omega. That is written as in this particular form, that is mentioned here. So theta can be written as omega t. Omega is known as the angular frequency or angular velocity, and t is the time taken. And phi is a new quantity, and that is known as a phase constant or simply a phase angle. So this is known as a phase angle. A phase angle will tell you in what phase are you with another wave, or what phase difference are there. You will study it mostly in detail in second PUC. But first, let's see. If there is one wave which is traveling like this, okay, this is wave number 1. Now imagine that there is one more wave which is traveling in the same direction. So that particular wave is traveling like this. Okay, how much is the phase angle difference between these two waves? That is, how differently are these two waves moving? That can be understood from this particular phase angle. Is this second wave moving in front or behind the initial wave? That particular detail can be obtained from the phase angle. Right now we say that, okay, since both of them are meeting at exactly the same places, the phase angle between them is 0. That is, there is no phase difference between them. Both of them are moving together. Even though the heights of the wave, that is the amplitude of the wave is different, both of them are in sync with each other. Both of them are moving together, which means they have no phase difference. But imagine that one wave is actually moving like this. It means that there is actually a phase difference between these two waves. So again, if a wave is leading or lagging behind another wave, are they traveling together? Is the crust and crust meeting? Is the trough and trough meeting? That particular relation can be analyzed from this particular phase angle. So that is why phase angle actually exists. So that much initial information is the only thing you need right now before we get to the velocity and acceleration of these particular wave functions. So first, again, just to refresh, x is the displacement, a is the amplitude, cos is the nature of the motion, omega t is nothing but the angular frequency, and phi is nothing but the phase angle between two independent waves. So again, this much are the initial information that you need before you get into the acceleration and velocity of these particular waves. So let's start with velocity. So we actually know that velocity is nothing but rate of change of displacement. So what is displacement? We just figured out that x is nothing but displacement, which is a cos omega t plus phi. So a cos omega t plus phi is the displacement of a simple harmonic motion, or simply a particle which is executing a simple harmonic motion. So when we differentiate that particular quantity, again which you will study in detail in second PUC, you will get the answer as, again, here you have to apply something that is known as a chain rule or a product rule you have to apply here. And then you can write down it as, that is dx by dt will be equal to, so this is a constant which will come right outside. Differentiating cos, you will get negative sign. So negative sign And omega t, again, if you differentiate omega t, omega will come right outside and the remaining quantity will be again omega t plus phi, because here again you have to apply the product rule in the case which derivative of the first plus second quantity into derivative of the first quantity. You have to apply the product rule, which you learn in detail in the second PUC. So again, if I do this particular derivative, this answer I'll get it as minus a omega sine omega t plus phi will be the answer I get, which is the equation for velocity of a particle which is executing a simple harmonic oscillation. So again, the initial thing you have to remember is that if you differentiate, let's say b cos x, okay, if you differentiate b cos x, then this b will be a constant which will come right outside, and if you differentiate cos x, the quantity you will be getting will be sine x and it will be negative. So negative sine x into b, or simply negative b sine x will be the final answer you're getting. That is why we have sine here and it is negative here, and why a came right outside. Similarly, when you differentiate omega t plus phi, you have to apply the product rule. Again, the derivative of a constant will be 0, and omega t divided by dt, you have to apply the product rule. So it will be omega into dt by dt, that is 1, plus t into d omega by dt, which is again 0. So the only quantity you will be getting is omega, which will be coming right outside of the equation. So minus a omega sine omega t plus phi will be the answer. Similarly, for acceleration, we can say that a is equal to dv by dt. So again, a is equal to d by dt of v. We already have an equation, that is minus a omega sine omega t plus phi. Same procedure we are going to repeat. We are going to differentiate these particular quantities, but again, minus 1, a and omega are constants which will come right outside of the equation, which means we can write that first here itself, minus a omega there, and then when you differentiate sine omega t plus phi, if you differentiate sine, you will get cos. So again, it will be cos, and here omega t, if you differentiate that, omega will come right outside, which means that into omega cos omega t plus phi. Omega into omega, that is minus a omega square cos omega t plus phi. So again, if I take this a with the cos, then I can say that this equation will be equal to minus omega square a cos omega t plus phi. And again, if you look really closely, this a cos omega t plus phi, it is nothing but the x, that is the displacement term we took initially. So I'm going to call this entire term as x. Then you have your equation as acceleration a is equal to minus omega square x. So this is where the equation for acceleration actually came. So that is why when we proved it for the first time, that k by m, I took it as omega square, because right now it resembles the equation which is acceleration. So wherever we see k by m, we are going to take it as omega square. So that is their particular relation. So we have an equation in terms of velocity and in terms of acceleration. But wait, this is only in terms of dv by dt. We can also take the second derivative of displacement and it will also give us acceleration. Now again, we have a relation in terms of v and we have a relation in terms of a, that is dv by dt and dx by dt. Now we also have one more equation which we stated as v is equal to omega into root of a square minus x square. So where did this particular equation came into effect? That particular equation came into effect through the following way, which I'm going to explain right now. So first, I'm going to write down x is equal to a cos omega t plus phi, which is our equation for SHM. And again, I'm going to take the square, which means x square is equal to a square cos square omega t plus phi. And again, From here, I am going to take the derivative. That is to find what is v square, which is equal to dx square by dt, and you will get it as, again, we know what is the equation for v. V is minus a omega. So minus a omega sine omega t plus phi. So again, if you square that, a square omega square sine square omega t plus phi will be the answer. And then from here, if I take this omega square to the left hand side, then I can write it as v square by omega square will be equal to a square sine square omega t plus phi. Now I'm going to call this one equation number 1 and this one equation number 2. Now what I'm going to do is that I'm going to add equation 1 and equation 2, because again, in the initial expression there was an a square minus x square, right? We don't know where it came from. So I'm just trying to add these two equations together and let's see where we enter. So I'm going to add, so x square plus v square by omega square, which will be equal to a square sine square omega t plus phi plus a square cos square omega t plus phi. So again, a square and a square are common. We can keep it outside and we can write this as a square into sine square omega t plus phi plus cos square omega t plus phi. Now, if you remember your trigonometric results, you will know that sine square theta plus cos square theta will be equal to 1, which means that sine square theta plus cos square theta will be equal to 1, and the only remaining quantity on the right hand side will be a square. So again, then we can say that x square plus v square by omega square is equal to a square. Or if I take this x square to the other side, I can say that v square by omega square is equal to a square minus x square. Now again, if I take this omega square also to that side, v square is equal to omega square into a square minus x square. Now if I take the root, then I can say that v is equal to omega into root of a square minus x square. This is the expression we wrote for an expression for velocity. So this way we can figure out what is the expression for velocity of an SHM also. And one small thing you have to remember is that we have the phase difference between velocity and acceleration, acceleration and displacement, velocity and displacement. So you don't have to necessarily prove or find out graphically what that means. You just have to know the values. Just for that particular reason, I'll just give you the values directly. So phase difference between v and x, that is velocity and displacement, will be equal to 90 degrees. And similarly, phase difference between a, that is acceleration and velocity, will also be equal to 90 degrees. And phase difference between acceleration and displacement will be equal to, the phase difference between these two will be equal to 180 degrees. So these will be the phase angle difference or phase difference between acceleration and velocity, and acceleration and displacement, velocity and displacement. So since you don't have to necessarily prove anything, I'm just directly giving you the phase values because that's the only thing that is going to be asked for your exams. So that's why it is given directly to you. But you have to know how you get acceleration and velocity. I hope you have understood how we get acceleration, velocity, what exactly is an oscillatory motion, what exactly is a periodic motion. In the coming classes, we'll discuss the important topics we have to learn in this particular chapter. And then until then, I hope you have understood everything here today. Thank you.